That single point of light is a galaxy filled with billions of stars. The Hubble Deep Field image revealed thousands of such galaxies in a patch of sky the size of a grain of sand held at arm's length, a humbling window into the sheer scale of the cosmos. Yet today, cosmologists are focused on a single number that threatens to unravel our entire picture of this vast universe. It is called the Hubble Tension, and it represents the most significant, puzzling discrepancy in modern science. The universe appears to be expanding at two different speeds. The rate we measure in our cosmic neighborhood stubbornly disagrees with the rate predicted by the ancient afterglow of the Big Bang itself. This is not a minor accounting error. It is a potential crack in the foundation of reality, a signal that our most trusted laws of physics might be incomplete. By the end of this exploration, you will understand the 25 compelling reasons why this single number has the world's top scientists utterly baffled and genuinely excited. Could a flaw in Einstein's universe point the way to a new kind of physics? What if everything we think we know about dark energy is wrong? How does it feel to live at the very edge of a scientific revolution? This conflict arises from two of the most solid pillars in all of cosmology. On one side, we have the local universe. To measure how fast space is stretching right now, astronomers use a brilliant cosmic ladder. Its first rung is built with stars called Cepheid variables. These are aging, giant stars that pulse with a regular, predictable rhythm. Their true brilliance is linked directly to the tempo of their heartbeat. Find a Cepheid, clock its pulse, and you know its true, intrinsic brightness. Compare that to how dim it appears from Earth, and you can calculate its distance with stunning precision. This is how we first measured the distance to other galaxies a century ago. Today, we climb higher. We use those Cepheids to calibrate the next rung, cosmic explosions known as Type 1, a supernova. These are thermonuclear blasts of dying stars that always release the same titanic amount of light. They are the ultimate standard candles, visible across billions of light years. By tracking these supernovae in galaxies whose distances we know from Cepheids, we can see how fast the universe's expansion is stretching their light, making it redder. This entire meticulous process is called the cosmic distance ladder, and it gives us a number for the current expansion rate. That number, from mission after mission, is about 73 kilometers per second per megaparsec. In simpler terms, for every 3.26 million light years you look out into space, galaxies appear to be racing away from us 73 kilometers per second faster. It is a precise, repeatable local measurement, but then we look back, way back to the very beginning. The second pillar comes from the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light, released when the universe was a mere 380,000 years old, is a frozen snapshot of the infant cosmos. By mapping its tiny temperature fluctuations with incredible detail, satellites like Planck have measured the contents and geometry of the early universe with phenomenal accuracy. From that pristine blueprint, using our established laws of physics, scientists can run the cosmic film forward. They can calculate exactly how the universe should have evolved over 13.8 billion years to become what we see today. This prediction yields an expansion rate. That number is about 67, not 73, 67. The discrepancy is small in number, only about 9%, but its implications are cosmic. It means the universe today is expanding significantly faster than our best theory of its infancy says it should be. We are not comparing rough guesses. We are comparing two Nobel Prize-crowned methods, each refined over decades, and they are telling us two different stories about the same reality. One is a direct measurement of the present. The other is a pristine record of the past, used to predict the present. They should match perfectly. They do not, and that is the heart of the tension. 9% may sound like a small difference, but in the precise world of cosmology, it is an earth-shattering chasm. This is not a rounding error or a slight miscalibration. The true weight of the Hubble tension is measured not in percentages, but in a unit called sigma. Sigma is the language of certainty, a statistical measure of how likely a result is to be just random noise. In many fields, a 2 sigma result might raise an eyebrow. A 3 sigma finding is considered evidence, but in physics, the bar for a genuine discovery is set astronomically high at 5 sigma. This means the probability that the observed discrepancy is merely a statistical fluke is less than 1 in 3.5 million. The tension between our local and early universe measurements has now soared past that 5 sigma threshold. Think about what that represents. It is the same standard of proof used to confirm the existence of the Higgs boson, the particle that gives others mass. It is the gold standard for declaring we have found something fundamentally new. When 2 methods, each built with meticulous care, disagree at this level of confidence, it screams that the problem is not with our instruments. The problem is likely with our understanding. This staggering statistical significance transforms the Hubble tension from an intriguing puzzle into a 5-alarm fire for theoretical physics. It forces every cosmologist to confront a daunting possibility. We are not just tweaking a decimal point in our equations. We might be standing at the edge of a paradigm shift, staring into a gap in reality that our current laws cannot explain. This robust local measurement does not stand alone. Its strength comes from a chorus of independent voices, each singing the same unsettling tune. Take the humble red giant star. At the end of their lives, these stars undergo a dramatic change, reaching a known peak brightness before fading. This makes them another kind of standard candle, a completely different tool from the pulsing Cepheids or exploding supernova. When astronomers used data from the Hubble Space Telescope to measure distances to red giants in nearby galaxies, they arrived at an expansion rate that aligned strikingly with the higher value. A separate ladder built with different stars reached the same unsettling height. Then there is the cosmic stopwatch, a method that bypasses stars entirely. It uses the warping of spacetime itself through a phenomenon called gravitational lensing. When a massive galaxy sits directly between us and a distant quasar, its gravity bends the quasar's light, creating multiple images of the same object. Because the light for each image takes a slightly different path around the galaxy, they flicker at slightly different times. By meticulously monitoring these time delays for years, projects like H0LICOW can geometrically triangulate the distances involved. It is a pure measurement of cosmic geometry, independent of any stellar physics. And consistently, these gravitational lensing time delays have pointed toward an expansion rate closer to the faster local value. Each of these methods has its own quirks and potential pitfalls. Red giant measurements must account for dust in galaxies. Gravitational lensing requires complex models of the foreground galaxy's mass. Yet their collective verdict is compelling. They are not all making the same mistake. They are different instruments in a cosmic orchestra, and while they may occasionally play a slightly off note, the symphony they produce is unmistakable. The higher expansion rate is not an artifact of one fragile technique. It is a signal being picked up by multiple independent receivers, all tuned to different frequencies of the universe. This convergence makes the tension impossible to ignore. It tells scientists that the problem almost certainly does not lie in our local measurements. The discrepancy is real, and its source must be sought deeper in the fabric of reality or further back in cosmic time. But if the local measurements are so robust, we must turn our gaze to the other side of the cosmic ledger, to the pristine record of the beginning. Here, the evidence is not just precise, it is almost unnervingly perfect. The European Space Agency's Planck satellite was a time machine of unparalleled sensitivity. For over 4 years, it stared into the deep cold of space, mapping the cosmic microwave background in more detail than ever before. What it captured was not a simple, uniform glow. It was a tapestry of the universe at 380,000 years old, imprinted with faint ripples of temperature, variations of mere millionths of a degree. These ripples are the cosmic seeds, the gravitational fingerprints of all the structure to come, every galaxy cluster and vast void we see today. Planck measured the precise size and distribution of these ripples with such exquisite accuracy that it allowed scientists to determine the universe's recipe, its fundamental ingredients, to within a fraction of a percent. We know from this single snapshot exactly how much ordinary matter, dark matter, and dark energy the infant universe contained. We know its geometry is flat to a razor's edge. Using our established laws of physics, primarily Einstein's theory of general relativity, we can take this perfect infant blueprint and press play. We can simulate the entire 13.8 billion-year evolution of the cosmos, watching dark matter clump, dark energy accelerate, and galaxies form. This forward projection yields a firm, unambiguous prediction for how fast the universe should be expanding today. Planck's prediction is 67. The precision is the problem. If Planck's data were fuzzy or uncertain, we could easily dismiss the tension as a measurement error, but its data is not fuzzy. It is arguably the most precise dataset in the history of cosmology. The satellite did its job flawlessly, giving us a crystal-clear picture of our cosmic origins. The fact that this crystal-clear picture, when interpreted through our best theories, predicts a present that does not match what we actually see, is what elevates this from a curiosity to a crisis. It means the conflict is not between a good measurement and a bad one. It is between two excellent, precise, and utterly contradictory views of reality. One is telling us the story of the universe as it was. The other is showing us the universe as it is, and the plot, according to our current physics, no longer makes sense. The very framework that predicts this lower expansion rate is the crown jewel of modern cosmology. It is known as the lambda cold dark matter model, or lambda CDM for short. This is our standard model of the universe, a set of equations and ingredients that has explained an astonishing range of cosmic phenomena with breathtaking accuracy. According to this model, the cosmos is composed of about 5% ordinary matter, the stars and planets and gas we see. 27% is an invisible, mysterious substance called cold dark matter, whose gravity sculpts galaxies and holds them together. And a whopping 68% is the even more enigmatic lambda, representing dark energy, the force causing the expansion of space to accelerate. This simple recipe, when plugged into Einstein's equations, has produced triumph after triumph. It perfectly accounts for the relative abundances of the lightest elements forged in the first few minutes after the Big Bang. It predicts the intricate cosmic web of galaxy clusters and vast voids we observe in the sky. It explains the subtle patterns in the cosmic microwave background down to the finest details Planck observed. For decades, lambda CDM has been the unshakable foundation, the theory that could do no wrong. But the Hubble tension is different. It is the model's first major, persistent failure. After correctly predicting so much about our universe, from its earliest moments to its largest structures, it now makes a firm prediction about the present-day expansion rate that our telescopes tell us is wrong. This is not a minor adjustment. It is like discovering a single, fundamental equation in a beloved physics textbook gives the incorrect answer every single time you use it, despite every other chapter being flawless. The model's very success makes this failure so profound and so troubling. We have built our entire understanding of cosmic history upon lambda CDM, and now, at the very end of that story, in the chapter we are living in right now, the numbers do not add up. The most straightforward answer is often the simplest. Perhaps there are no new laws of physics. Maybe, after all this, we have just made a mistake. This is the realm of systematic errors, hidden flaws in our measurements that could be throwing everything off. Every scientist's first instinct when faced with a discrepancy is to check their instruments, and the hunt for such errors in the Hubble tension has been exhaustive. On the local side, the cosmic distance ladder is a chain, and its strength depends on every link. The first critical link is the calibration of Cepheid variables within our own Milky Way. To know how bright a Cepheid truly is, we must know its distance with absolute certainty. For decades, this was done using a geometric method called parallax, measuring the tiny apparent shift of a star as Earth orbits the Sun. But these shifts are minuscule at the very limit of what our telescopes can detect. Could there be a subtle, consistent bias in how we measure these foundational distances? Even a small error here would propagate up the entire ladder, magnifying as we climb to supernova in distant galaxies. Another persistent worry is cosmic dust. Our galaxy and the galaxies we observe are filled with microscopic grains that float between the stars. This interstellar dust does not block light completely. It reddens and dims it like a dirty windshield on a car. If we underestimate how much dust lies between us and a Cepheid star, we would think the star is dimmer and therefore farther away than it truly is. This would throw off our entire calculation of the expansion rate. Teams have spent years modeling dust with increasing sophistication, using multiple wavelengths of light to see through the haze, and while it can adjust the numbers slightly, it has not closed the gap. On the early universe side, the Planck data seems almost immune to error, but it is not invincible. The cosmic microwave background is not the only light coming from that direction. Our own Milky Way galaxy glows with radio waves and dust emission, and there are countless distant galaxies in the foreground. Separating the pristine cosmic signal from this celestial clutter is a monumental task of data processing. Could a subtle misestimation of this foreground contamination slightly alter the pattern of the ancient ripples and thus change the predicted expansion rate? Furthermore, the satellite's instruments themselves, though exquisitely calibrated, have their own tiny, complex behaviors that must be perfectly understood and removed. The teams behind both the local and early universe measurements are not naive. They are their own fiercest critics, and they have combed through every conceivable source of error for over a decade. They have cross-checked with independent methods, reanalyzed data with different assumptions, and subjected their work to relentless peer review. The result of this soul-searching is clear. No one has found a single, convincing systematic error large enough to bridge the 9% divide. While small adjustments from better dust models or improved calibrations are always possible, they tend to move the measurements in tiny increments, not the giant leap required to make 73 and 67 agree. The persistence of the tension, even as our tools grow sharper, suggests the problem is not in our mirrors and detectors. It is likely written into the cosmos itself. This relentless hunt for errors leads us to a thrilling and unsettling conclusion. Perhaps the measurements are not wrong. Perhaps our universe is. This is the phantom of new physics, the electrifying possibility that the Hubble tension is not a problem to be solved, but a clue to be followed. If both the local and early universe measurements are as precise as they seem, then the only logical explanation is that our cosmic recipe book, the lambda cold dark matter model, is missing a key ingredient, or that one of its fundamental instructions is flawed. We are not talking about adding a pinch of salt to the soup. This would be discovering an entirely new spice. The tension in this light transforms from a frustrating discrepancy into a brilliant beacon. It is a signal from the cosmos itself, pointing directly at a gap in our understanding of reality. For theoretical physicists, this is the most exciting kind of mystery. It is not a dead end, but a doorway. The discrepancy tells them exactly where to look, what equations to challenge, and which sacred cows of cosmology might be ready for reconsideration. Could dark energy, that mysterious force accelerating the expansion, be more complex than a simple constant? Could it change over time or interact with dark matter in ways we never anticipated? Or does the fault lie deeper in Einstein's theory of gravity itself? While general relativity has passed every test with flying colors for a century, the Hubble tension might be its first genuine crack, a hint that on the vast scales of the entire cosmos, gravity behaves in a subtly different way. This phantom of new physics is what keeps scientists up at night, not with worry but with a burning curiosity. The universe has handed us a puzzle, and its solution might rewrite the textbooks. The most tantalizing candidate hiding in that gap is dark energy itself. For decades, our standard model has treated it as the simplest thing possible, a constant. We call it lambda, the cosmological constant, a fixed energy density woven into the very fabric of space that never changes. It is the steady pressure causing the cosmic acceleration we see today. But what if that is the mistake? What if dark energy is not a constant feature of the cosmos, but a dynamic one? This idea is known as evolving dark energy, and it is a direct assault on the simplicity of our standard model. Imagine dark energy not as a still lake, but as a river whose current can speed up or slow down over cosmic time. If dark energy was more potent in the universe's adolescence, it would have given expansion an extra push earlier on. That ancient, stronger shove would have stretched the infant universe more than our constant lambda model predicts. To make the cosmic microwave background from that faster-stretching early universe look exactly like the pristine snapshot Planck observed today, we would have to adjust our model's other parameters. Crucially, one adjustment would be to lower the predicted present-day expansion rate. Suddenly, the math could begin to bend. A stronger dark energy in the past could make the early universe's prediction for today's expansion drop from 67 down toward an even lower number, which would paradoxically make the gap with our measured 73 even wider. That does not sound helpful, but the real magic happens when you consider the entire cosmic timeline. An evolving dark energy does not just change the starting push, it changes the entire race. If that early strength faded as the cosmos aged, the expansion would have coasted more in the middle epochs before the dark energy we measure today took over. This altered expansion history could, in principle, twist the cosmic distance ladder in just the right way. It could make the distances we measure with supernovae correspond to a faster present-day expansion, even if the average expansion over all time was slower. It is a cosmic sleight of hand where changing the rules of the game in the past changes how we score the present. The appeal is powerful, but the cost is immense. Introducing evolving dark energy shatters the elegant simplicity of lambda. It replaces a single number with a whole new equation, a new field of physics we have no guide for. We would need to explain what this energy is, why it evolves, and what triggers its changes. It transforms dark energy from a static backdrop into an active, mysterious character in the cosmic story, one whose motives we do not understand. A more radical idea than evolving dark energy has emerged, a specific and fleeting phantom from the dawn of time. Theorists call it early dark energy. This is not the dark energy we live with today, but a hypothetical burst of repulsive force that existed only for a cosmic instant, in the first few 100,000 years after the Big Bang. Imagine it as a temporary cosmic booster rocket, firing fiercely in the universe's infancy before sputtering out completely, leaving behind the quieter, constant dark energy we measure now. Its entire existence would have been confined to the era before the cosmic microwave background was released, a ghost in the machine of creation that vanished before the first atoms even formed. Its proposed effect is subtle but profound, targeting the very ruler Planck used to measure the early universe. That ruler is the sound horizon. In the hot, dense plasma of the infant cosmos, particles of light and matter were locked in a tight embrace, creating a fluid that could transmit pressure waves. These waves raced outward from every density ripple at nearly the speed of light, like ripples from a stone dropped in a pond. Then, at 380,000 years old, the universe cooled enough for atoms to form, freeing the light. That moment froze the largest of these pressure waves in place, imprinting their preferred size onto the cosmic microwave background as a characteristic peak. Planck measured this frozen wave size, the sound horizon, with incredible precision. It is a standard ruler etched into the sky. From its apparent size in the sky, we can calculate distances in the early universe and thus infer the expansion rate. Early dark energy proposes to shrink that ruler. If this temporary repulsive force was active during those first few 100,000 years, it would have given the expansion of space an extra, fleeting kick. A faster expanding universe would have diluted the primordial plasma more quickly, making it harder for those pressure waves to travel. The ripples would have had less time to grow before the universe became transparent. The result would be a sound horizon that is physically smaller than our standard model predicts. When Planck looks at the sky, it would still see a perfectly clear pattern of ripples, but the scale of that pattern would correspond to a smaller physical ruler. If scientists then take this smaller ruler and, unaware of early dark energy, plug it into their standard equations to run the cosmic film forward, they would get a prediction for today's expansion rate that is too low. They would mistakenly infer a Hubble constant of 67. But if the ruler was truly smaller, then the real expansion history needed to produce the cosmos we see would have to be different. Correcting for this phantom booster rocket could allow the predicted expansion rate to climb, potentially meeting the higher local measurements halfway. It is an elegant fix in theory, a single, short-lived ingredient that alters the starting conditions just enough to make both the pristine past and the frantic present agree. Yet it remains a phantom, a mathematical possibility waiting for a shred of direct evidence from the dawn of time. But what if the problem is not with one dark component, but with their relationship? Our standard model treats dark matter and dark energy as perfect strangers in a shared universe. Dark matter clumps together under gravity, providing the cosmic scaffolding for galaxies. Dark energy, as a constant, acts as a smooth, repulsive background that stretches space itself. They are modeled as completely independent, two actors on a stage who never exchange a single glance. This might be our most profound oversight. Reason 10 invites us to consider a radical possibility, that these two dominant yet invisible forces of our cosmos might actually talk to each other. They could interact. Imagine if dark matter, the gravitational glue, could slowly leak its essence into dark energy, the repulsive force. Or perhaps dark energy decays, seeding new dark matter over eons. This energy transfer would rewrite the cosmic energy budget over time. In the standard model, as the universe expands, dark matter dilutes, becoming less dense, while the density of constant dark energy stays the same, allowing it to eventually dominate. But if they are coupled, that story changes dramatically. If dark energy is slowly feeding off dark matter, then in the past, dark matter would have been more abundant and dark energy weaker. This altered balance would change how fast the universe expanded during its Middle Age, the very epoch that connects the early cosmic microwave background to our local supernova measurements. A different expansion history could stretch the cosmic distance ladder in a unique way, potentially aligning the early and late universe expansion rates. This is not a minor tweak. It introduces a new dialogue into the heart of darkness, a fundamental interaction that our physics has never accounted for. It suggests the dark sector is not a collection of inert ingredients, but a dynamic, evolving ecosystem with its own hidden rules. Finding evidence for such a conversation would be like discovering that two fundamental forces of nature, thought to be separate, are secretly intertwined, forcing us to redraw the entire blueprint of cosmic evolution. Our cosmic recipe has another ghostly ingredient, one we have barely begun to weigh: Neutrinos are the universe's ultimate ghosts, subatomic particles so light and weakly interacting that trillions pass through your body every second without a trace. For most of cosmology's history, they were considered massless, mere cosmic speedsters that flew freely through the newborn universe, their only effect being to smooth out the primordial plasma slightly. But we now know neutrinos do have mass, an astonishingly tiny one, and in the delicate balance of cosmic evolution, even a whisper of extra mass can shout. The total heft of all neutrinos influences how the cosmic structures we see today were able to clump together under gravity. Heavier neutrinos streaming at near light speed would have acted like a cosmic wind, washing over the tiny density ripples in the early universe and smoothing them out, making it harder for galaxies to form. This leaves a specific imprint on both the cosmic microwave background and the large-scale distribution of galaxies we see. The Planck data already places an upper limit on the total neutrino mass, but what if that limit is wrong? What if neutrinos are collectively heavier than we think? Adding more neutrino mass into the early universe models would change how we interpret the Planck snapshot. To still end up with the galaxy clusters we observe today, other parameters in the model would have to shift to compensate, and one of those parameters is the predicted expansion rate. It is a complex cosmic balancing act where adjusting the weight of one ghostly particle could nudge the Hubble constant prediction upward. Even more speculative is the possibility of sterile neutrinos, a hypothetical fourth type that does not interact via any force except gravity. These would be shadows of shadows, influencing the cosmos only by their gravity and their effect on the early universe's expansion rate. If they exist, they would be a wild card from the realm of particle physics, dealt directly into the cosmic game and potentially reshuffling the deck enough to ease the tension. This connection is profound. It means the key to the largest puzzle in the universe might be hidden in the properties of the smallest, most elusive particles ever discovered. Geometry holds the key to the cosmos, and our standard model locks it into a perfect, unwavering flatness. This is not flat like a table, but flat in the grand, geometric sense that parallel lines never meet and the angles of a triangle always add up to 180 degrees. A flat universe is the direct prediction of cosmic inflation, that blistering exponential expansion in the first fraction of a second after the Big Bang. It is also what the Planck data, with its razor-sharp measurements of the cosmic microwave background ripples, overwhelmingly confirms. The universe is flat too, within a breathtaking margin of error, about 0.2%. But what if that last sliver of uncertainty is not just noise? What if the universe possesses a whisper of curvature, a cosmic bend so subtle our best instruments can barely hint at its presence? This is the curvature conundrum. Introducing even a tiny amount of positive curvature, like a four-dimensional sphere, would warp our cosmic perspective. In a positively curved universe, light would travel along great circles, bending inward. This would make distant objects, like the supernovae we use in our distance ladder, appear slightly farther away than they truly are in a flat universe. If we mistakenly assumed flatness while measuring them, we would infer an expansion rate that is too high. That sounds promising. It could potentially explain the faster local measurement. But the cosmic microwave background is the ultimate referee. The pattern of its ripples is exquisitely sensitive to curvature. A positively curved universe would predict a different pattern of hot and cold spots than what we see in the pristine Planck data. To make a curved universe fit that perfect snapshot, you would have to start twisting other dials in the model, like the amount of dark matter or the behavior of dark energy, often pushing them into uncomfortable, unrealistic values. It becomes a cosmic house of cards where adjusting one parameter to fix the Hubble tension makes three others wobble dangerously. Some analyses have found that allowing for a slight curvature can indeed ease the tension between early and late universe measurements, but the cost is a universe that no longer perfectly matches other observations like the clustering of galaxies. It trades one mystery for several others, forcing theorists into a delicate and unsatisfying balancing act where the cure may be worse than the disease. A fundamental truth often gets lost in the name itself. The Hubble constant is not and has never been truly constant. This is a crucial point of public confusion, and it lies at the very heart of the mystery. The term constant here is a cosmic misnomer, a historical artifact from a simpler time. What we are actually measuring is the Hubble parameter, a value that describes how fast space is stretching at any given moment in cosmic history. The so-called constant, denoted as h0, is specifically its value today, right now, in this present epoch of the universe. In the past, during the universe's fiery youth, the expansion rate was far more frantic. In the distant future, as dark energy's influence grows, it will likely settle into a different, steady pace. The Hubble constant is a single snapshot, a speedometer reading for the cosmos at this precise moment in its 13.8 billion-year journey. The tension arises because we have two magnificent cosmic clocks, and they are giving us two different times for the present. One clock was set and wound at the very dawn of time, its mechanisms frozen into the cosmic microwave background. By reading its intricate gears, we can calculate what time it should be now. The other clock is built from the motions of galaxies in our recent cosmic neighborhood, a direct observation of the current tick and tock. Both are exquisite timepieces crafted with Nobel Prize-winning precision. Yet one says the present expansion rate is 67, while the other insists it is 73. This is not a debate about the past or the future. It is a direct conflict about the state of the universe you and I live in today. The challenge, then, is one of cosmic connection. Can we draw a smooth, unbroken line from that pristine infant snapshot to the bustling galactic metropolis we see outside our window, using only the physics we know and trust? The Hubble tension screams that we cannot, that somewhere along that epic timeline, our story of the universe has taken a wrong turn or missed a hidden chapter entirely. Measuring the universe is an act of breathtaking audacity. We are trying to determine the distance to a star in another galaxy, a pinpoint of light so faint it pushes our greatest telescopes to their absolute limits. The challenge is not just one of engineering, but of cosmic perspective. Imagine trying to judge the true distance to a single candle flame from 10 miles away with nothing but your naked eye. You cannot pace it out, you cannot send a probe. Your only clue is how dim the flame appears. But what if that particular candle is hidden behind a wisp of fog? What if its wax burns with a slightly different chemistry, making it intrinsically brighter or fainter than a standard candle? A tiny misjudgment about its true brightness leads to a colossal error in calculating its distance. This is the daily reality for astronomers building the cosmic distance ladder. Their candle flames are the Cepheid variable stars pulsing rhythmically in galaxies millions of light-years away. For decades, the Hubble Space Telescope dedicated a staggering portion of its precious observing time to this single, monumental task. It would stare at a single, distant galaxy for orbit after orbit, patiently collecting photons from individual Cepheids, trying to lock down the precise timing of their pulses and their apparent brightness. Each measurement was a battle against noise, against cosmic dust, against the limits of optics, and this was just the first, foundational rung. Those Cepheid distances then had to be used to calibrate the next, even more distant rung, the titanic explosions of Type 1, a supernova. A single misstep on a lower rung, a slight bias in how we account for interstellar dust in one galaxy, propagates upward. It magnifies, twisting the entire ladder. The local measurement of the Hubble constant is not a single number from a single instrument. It is the final product of a 30-year odyssey, a fragile chain of inferences built one precarious observation at a time. The fact that multiple independent teams, using slightly different methods and battling different systematic errors, keep arriving at the same stubbornly high number is what gives the result its immense weight. The tension persists not in spite of this painstaking work, but because of it. This entire cosmic calculation rests on a single, fundamental measurement etched into the ancient light. It is called the sound horizon, and it is the most important ruler in the universe. To understand it, we must go back to the cosmos before it was even 380,000 years old. At that time, the universe was not transparent, but a searing, opaque fog. Ordinary matter existed as a plasma of protons and electrons, and light was trapped within it, constantly bouncing off the charged particles. This hot, dense soup could carry sound waves, but these were not like sounds we hear. They were vast pressure waves, ripples of density moving through the entire cosmic medium at a significant fraction of light speed. Think of it as a single, universe-spanning ocean, with tsunamis of compression and rarefaction racing outward from every tiny seed of overdensity. These waves traveled until the moment of recombination, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, the fog cleared. The light which had been trapped was set free, becoming the cosmic microwave background we see today. But the sound waves were frozen in that instant. The distance a pressure wave could travel from the beginning of time until that moment of liberation defines the sound horizon. It is a specific physical scale, like the radius of the largest ripple in a pond when the water suddenly turns to ice. This scale was then imprinted onto the hot and cold spots of the cosmic microwave background. The most common distance between slightly hotter regions and slightly colder regions in the Planck map corresponds directly to that frozen sound wave. So we have a standard ruler of known length woven into the fabric of the first light. By measuring its apparent angular size on our sky, cosmologists can perform a simple geometric calculation. It is like holding a ruler of known length at arm's length and measuring the angle it subtends to judge its distance. If the ruler appears smaller, it must be farther away. The apparent size of the sound horizon in the sky tells us the distance to the cosmic microwave background, and from that distance and the redshift of that ancient light, we can deduce the expansion history and predict the Hubble constant today. The Planck team did this with phenomenal precision, arriving at 67. The tension, therefore, whispers a disturbing possibility. Either this cosmic ruler is not the standard length we believe it to be, or our measurement of its apparent size in the sky is somehow biased. Could something in the early universe have altered the speed of sound, changing how far those waves traveled? Or is there something between us and the ancient light, warping our view, making this fundamental ruler appear a different size than it truly is? The integrity of our entire cosmic timeline hangs on the perfection of this single, frozen echo. The sound horizon is not the only cosmic measurement feeling the strain. As scientists have probed deeper, they have uncovered other, quieter murmurs of discontent within the data. These are lesser-known tensions, statistical whispers that do not yet scream with 5 sigma certainty, but together they form a troubling chorus. One of the most persistent is known as the S8 tension. While the Hubble constant tells us how fast the universe is expanding, S8 describes how lumpy it is, how much matter has clumped together into galaxies and clusters over time. It is a measure of cosmic structure. We can predict S8 from the pristine blueprint of the cosmic microwave background, just like we predict the Hubble constant. And we can measure it directly in the late universe by surveying the positions and shapes of millions of galaxies. According to Planck's early universe data, the universe should be slightly more smooth, with matter a bit less clumped than what our galaxy surveys actually find. The discrepancy is smaller, hovering around 2 or 3 sigma, but it is stubborn. This is crucial because it points to a potential problem in a different part of the cosmic story. The Hubble tension is about the expansion history, the timeline of the universe's size. The S8 tension is about the growth history, the timeline of how structures within it formed. In our standard model, these two histories are intimately linked by gravity. If the model is correct, they should tell one consistent story. The fact that we see hints of a mismatch in both the expansion and the growth of structure suggests the issue may run deeper than a single wrong number. It hints that the flaw might be in the engine of cosmic evolution itself, perhaps in how gravity operates on the largest scales or in the fundamental properties of dark matter. The Hubble tension is the loudest alarm bell, but these other anomalies are the faint, flashing warning lights on the same dashboard. They raise a haunting possibility. We are not looking at one isolated puzzle. We might be witnessing the first cracks in a much broader foundation, signs that our beautifully simple lambda cold dark matter model is beginning to fray at multiple edges at once. Into this high-stakes standoff, a powerful new judge has arrived. The James Webb Space Telescope, with its golden mirror and profound infrared vision, was built to see further back in time than any instrument before it. Yet one of its first and most critical missions was to look right next door at the very foundation of our cosmic distance ladder. Hubble's optical eyes, as powerful as they were, struggled with a persistent foe, cosmic dust. Those crucial Cepheid variables, the pulsating stars we use to calibrate all distances, often sit in crowded, dusty regions of their host galaxies. Dust scatters and reddens blue light more than red light, making stars appear dimmer and redder than they truly are, like a distant street lamp in a thick fog. This introduced a nagging uncertainty into Hubble's measurements. Could better dust correction finally lower the expansion rate and ease the tension? Webb was designed to cut through that fog. Its infrared sensors see light that slips more easily through dust clouds. By observing Cepheids at longer wavelengths, Webb can measure their true brightness with far less contamination. More than that, it can simultaneously observe a completely different kind of standard candle in those same galaxies, the tip of the red giant branch. These are old, cool stars that all reach the same peak brightness before they fade. It is like having two independent witnesses to the same crime scene, each with a different story to tell, but Webb can hear them both at once with crystal clarity. The astronomical community held its breath, hoping Webb's pristine data would act as a definitive tiebreaker. The early results are now in, and they have sent a shockwave through cosmology. Webb's measurements of Cepheids and red giants are not only more precise, they are in stunning agreement with Hubble's earlier, higher value. The telescope's sharper vision has eliminated some of the largest potential systematic errors, tightening the error bars on the local expansion rate and making the discrepancy with the early universe prediction even more statistically robust. This was not the resolution anyone expected. The new hope has not brought peace, it has deepened the war. By confirming the higher local rate with unprecedented confidence, the James Webb Space Telescope has effectively ruled out a major class of mundane explanations. The problem is not in Hubble's dusty lenses. The tension is real, it is persistent, and it is now etched into the data of our most advanced observatory. The universe, it seems, is not backing down from its contradictory story. Even the sound of the universe can become a ruler. In 2017, a new chapter in astronomy opened not with a flash of light, but with a ripple in spacetime. For the first time, the LIGO and Virgo observatories detected the gravitational waves from a collision of two neutron stars, the incredibly dense corpses of massive stars. This cosmic crash did more than shake the fabric of reality. It offered a completely new way to measure the cosmos, one that needs no candles, no ladders, and no assumptions about stellar physics. We call them standard sirens. The concept is beautifully direct. As two neutron stars spiral inward and merge, they emit a crescendo of gravitational waves, a specific chirp that grows in frequency and amplitude. The shape of this waveform tells us exactly how massive the objects were. Crucially, the strength of the gravitational waves that finally reach Earth, their amplitude, depends on the energy released in the merger and critically on how far the event is from us. A louder signal means a closer source, a fainter signal means a more distant one. By analyzing the waveform, scientists can extract a direct distance to the merger, pure geometry written in the language of spacetime itself. But to get the expansion rate, we need one more piece, the speed, that came from the traditional telescopes. The same collision produced a brilliant flash of light across the spectrum, a kilonova. By identifying the host galaxy of this optical fireworks show, astronomers could measure its redshift, how much its light is stretched by the expanding universe. In one extraordinary event, we had both a direct distance and a redshift, a complete data point for the Hubble constant. The result from that first binary neutron-star merger was tantalizing. While its uncertainty was large, its central value leaned toward the higher local universe measurement. Since then, more detections, including mergers of black holes which lack an optical counterpart, have been analyzed using statistical methods. The growing collection of standard siren data is beginning to carve out its own path on the cosmic graph, and its trajectory is pointing stubbornly away from the early universe prediction and toward the faster expansion rate. This is not just another vote, it is a vote from an entirely different electorate. Gravitational wave astronomy operates on principles independent of the electromagnetic tricks of light, free from the worries of interstellar dust or the complex life cycles of stars. If both the traditional distance ladder and the new gravitational wave sirens are singing the same high note, the chorus against our standard model of the universe becomes almost impossible to dismiss as mere instrumental error. The sheer persistence of this cosmic contradiction has ignited a theoretical gold rush. In the corridors of physics departments and the pages of online archives, the Hubble tension has become something of a full employment act for theorists. With the stubborn data refusing to yield to simple fixes, the field has erupted into a creative frenzy, a marketplace of ideas where the wild and the wonderful are given serious consideration. The goal is no longer just to explain the discrepancy, but to imagine entirely new chapters for the cosmos. Some are taking aim at the bedrock itself, proposing modifications to Einstein's theory of gravity. These are not wholesale rejections, but subtle tweaks for the largest scales, ideas with names like scalar tensor theories or F of R gravity. In these models, the strength of gravity itself might have been different in the early universe or in the vast emptiness between galaxy clusters, subtly altering the expansion history in just the right way to bridge the gap. Others are dreaming in more exotic terms, suggesting the early universe underwent a phase transition we never knew about, a sudden shift in the properties of dark energy or dark matter that left a hidden imprint. Perhaps a new field of particles, undiscovered and strange, briefly dominated the cosmos, giving expansion an extra kick before vanishing without a trace. Then there is a particularly mind-bending idea that turns the problem inward. What if the tension is not about the universe, but about our place within it? This is the Hubble bubble hypothesis. It suggests our local region of the cosmos, out to a few hundred million light-years, might be unusually empty, a vast underdensity in the cosmic web. If we are living in a local void, then galaxies on the edge of this bubble would be rushing away from us faster than the true cosmic average, like driftwood caught in an outgoing tide. Our local measurements would then be skewed, giving us an inflated sense of the universe's true expansion rate. We would be cosmic provincials, mistaking our quiet neighborhood for the entire bustling metropolis. The very fact that such a diverse and speculative landscape of ideas is being actively explored is a testament to the depth of the crisis. It is a sign that scientists are willing to question everything, from the laws that govern the cosmos to our own special place within it, all in pursuit of a universe that makes sense again. This relentless clash of data forces us to ask a deeper, almost philosophical question. Is cosmology, the science of the entire universe, actually in a state of crisis? The word itself carries weight, suggesting a field on the brink of collapse, its foundations crumbling. But in science, a crisis is not a failure, it is the most fertile ground for discovery. Look back through history. For centuries, the comfortable consensus placed Earth at the center of the cosmos, until the meticulous observations of Tycho Brahe and the bold calculations of Kepler created a tension so severe it shattered that worldview, leading to the Copernican revolution. Later, the serene laws of classical physics predicted that a hot object should emit infinite ultraviolet radiation, a nonsensical result called the ultraviolet catastrophe. That glaring discrepancy was the direct catalyst for the birth of quantum mechanics, a theory that rewrote our understanding of reality at its smallest scales. In every case, it was not the elegant, working model that drove progress, but the stubborn, embarrassing anomaly that refused to go away. The Hubble tension is our generation's ultraviolet catastrophe. It is a signal that our beautifully polished model of the cosmos, lambda cold dark matter, for all its stunning successes, has met a reality it cannot digest. This is not a sign that science is broken, but proof that it is working exactly as it should. A genuine, persistent discrepancy is infinitely more valuable than a comfortable, unchallenged consensus. Consensus can breed complacency, but tension breeds creativity. It forces scientists to question their most cherished assumptions, to double-check their work with obsessive rigor, and to dream with radical audacity. The very fact that we can identify this 9% gap, that we can measure the universe with such precision that we can even have this argument, is a monumental human achievement. So no, cosmology is not in a crisis of collapse. It is in a state of exhilarating, productive turmoil. The foundation is not crumbling, it is being stress-tested, and the cracks we are seeing are not signs of impending ruin, but invitations to dig deeper and discover what stronger, stranger materials lie beneath. The ultimate resolution may not come from rethinking the past, but from an unprecedented flood of new observations. We are standing on the brink of a data revolution in cosmology, one that will transform our fuzzy snapshot of the universe into an ultra-high-definition movie. A new generation of observatories is poised to launch, each designed to attack the Hubble tension from a different, powerful angle. The European Space Agency's Euclid mission is already in space, its wide-eyed survey mapping the shapes and positions of billions of galaxies across cosmic time. It will not just count them, it will measure how their light is subtly warped by the invisible webs of dark matter in between, a technique called weak gravitational lensing. This will give us an exquisitely detailed picture of how cosmic structure has grown, providing a crucial independent test of the S8 tension and the dark matter framework that underpins our entire model. Then comes NAS, a Nancy Grace Roman Space Telescope, a powerhouse with a field of view 100 times larger than Hubble's. Roman is built for cosmic statistics. It will discover thousands of new Type 1 supernova, building a distance ladder with such immense numbers that random errors will vanish. More importantly, it will find them across a vast range of distances, allowing us to chart the expansion rate not just today, but at many different moments in the universe's middle age. We will see the curve of cosmic acceleration in exquisite detail. On the ground, the Vera C. Rubin Observatory will perform a similar feat on a monumental scale. Its gigantic mirror will scan the entire southern sky every few nights, discovering millions of supernovae and cataloging the positions of tens of billions of galaxies over a decade. This torrent of data will let us measure not just the Hubble constant, but how it has changed over the last several billion years. This is the key. These missions are not just aiming for a more precise number for today's expansion. They are building a forensic timeline. By mapping the entire expansion history of the universe with unprecedented fidelity, they could pinpoint the exact cosmic epoch when the universe's behavior began to drift away from the predictions of lambda cold dark matter. Did the divergence start recently, in the last few billion years as dark energy took hold? Or did it begin much earlier, hinting at a flaw imprinted in the first chapters of the story? This data deluge will either corner the standard model, revealing the precise moment it breaks down, or it will reveal subtle, hidden correlations in the existing data that finally allow the early and late universes to reconcile. The Hubble tension will not be solved by a single eureka moment, but by the relentless clarifying pressure of a trillion new data points. At its heart, this cosmic standoff presents a profound philosophical battle, one fought in the minds of every scientist studying it. On one side stands the venerable principle of Occam's razor, the idea that the simplest explanation is usually the correct one. In this case, the simplest path is to assume we have overlooked something, that a hidden systematic error still lurks in the data. This is the cautious, conservative approach, and it carries little professional risk. A scientist who meticulously finds and fixes a calibration error in a telescope or a subtle bias in a data pipeline is hailed as thorough, a guardian of rigor. Their work strengthens the existing edifice of knowledge. On the other side lies the thrilling, treacherous frontier of new physics. To propose that the universe contains an unknown force, a new particle, or a modification to gravity is to venture into complexity. It is a high-risk, high-reward endeavor. A theorist who champions an exotic model to solve the Hubble tension stakes their reputation on an idea that may be beautiful but could be utterly wrong. If a mundane error is later found, their complex solution collapses, and with it, perhaps, a career's worth of focus. This human drama infuses the technical puzzle with palpable tension. Entire research groups have spent years and millions of dollars in grant money pursuing these divergent paths. One team will dedicate a graduate student's entire PhD to painstakingly remeasuring the parallax of a single Cepheid variable star, chasing a potential error of a fraction of a percent. Another will invest the same amount of time and passion into crafting intricate equations for an early dark energy field that vanished 13 billion years ago. Both are essential. The error hunters keep the field honest, ensuring we do not chase phantoms born of our own mistakes. The theorists provide the imaginative leaps, the new maps for territory we have not yet explored. The Hubble tension has thus become a scientific crucible, testing not just our models of the cosmos, but the very process of how we do science under pressure, when the stakes for understanding reality could not be higher. This abstract number, this cosmic discrepancy, matters precisely because it is not just about astronomy. It is a direct line to the most profound questions humans have ever asked. Where did all of this come from? What is the universe ultimately made of? And what will its final fate be? The Hubble tension is not a technical squabble for experts. It is a crack in the answer key to existence itself. When scientists argue over a 9% difference in the expansion rate, they are really debating the entire life story of reality, from its first fiery breath to its last cold whisper. That story belongs to all of us. This is why the mystery holds such incredible power for public engagement. It transforms the vast, intimidating cosmos into a gripping detective story where every viewer can be an armchair sleuth. We are not passive observers, we are witnesses to a live investigation, one where the clues are written in ancient light and the suspect could be a flaw in Einstein's universe. The suspense is real and palpable. One day, perhaps sooner than we think, a headline will flash across the world. It might read, "Hubble tension solved, new force of nature discovered." In that instant, the esoteric becomes epochal. A number on a graph in a scientific paper would translate into a fundamental rewriting of the laws of physics. It would mean that our species, from our tiny planet, decoded a secret the universe had kept for 13.8 billion years. That potential eureka moment, the sudden shift from confusion to clarity, is a shared human triumph. It reminds us that the greatest mysteries are not locked away in textbooks, but are shining above us every single night, waiting for a curious mind to connect the dots. Yet the true prize shimmering at the end of this long, difficult road is not merely a fix for a single number. It is the promise of a grander vision, Imagine a single, elegant framework that could cradle the entire cosmic story, from the quantum spark of inflation to the vast, accelerating emptiness of the far future. This is the unifying dream that fuels every late night and every complex calculation. Resolving the Hubble tension could be the key that finally unlocks a new standard model of cosmology, a complete theory of the universe on its largest scales. Our current model, lambda cold dark matter, is a brilliant patchwork. It takes the known laws of particle physics, stitches them to Einstein's gravity, and then bolts on two mysterious ad hoc components, dark matter and dark energy, to make the equations fit the observations. It works, but it feels like a temporary fix, a list of ingredients without a recipe explaining why they are there or how they truly interact. The tension is the universe pointing at a loose thread in that patchwork. Pulling on it might not unravel the whole quilt, but it could reveal the pattern for a far more beautiful and integrated tapestry. A new, complete theory would not just make 73 and 67 agree. It would naturally explain why dark matter is cold and collisionless, why dark energy has the precise strength it does, and how the violent exponential expansion of inflation seamlessly handed off to the slower, matter-dominated expansion that built galaxies. It would weave these disparate epochs and ingredients into a single, coherent narrative, governed by a deeper set of principles we have not yet glimpsed. This would be a unification akin to the standard model of particle physics, which brilliantly describes three of the universe's fundamental forces and all known particles in a single mathematical language. But this would be a standard model for the cosmos itself, a theory of everything on the grandest possible stage. It would tell us not just what the universe is made of, but how its entire history unfolds from first principles. The Hubble tension in this light is not a crisis, it is a compass. It is the universe giving us a very specific, very precise clue about where our current understanding falls short. By following that clue with relentless curiosity, we are not just solving a puzzle. We are chasing the dream of seeing the cosmos in all its bewildering complexity as a single, breathtaking equation. That final reason might be the most important of all. The Hubble tension is a masterclass in cosmic humility. For a century, we have chased this single number, the Hubble constant, with ever more brilliant machines and ever more elegant theories. We have built telescopes that see the first light of creation and detectors that feel the shudders of colliding black holes. Our theoretical models have predicted the universe's history with a confidence that bordered on arrogance. Yet here we are at the pinnacle of our scientific power, staring at a 9% gap that refuses to close. This is not a sign of failure, but a vital reminder. The universe is under no obligation to be simple or to conform to our most beautiful ideas. It is a reminder that for all our maps and measurements, we are still explorers in a vast, unknown territory. And the most exciting discoveries often begin with a stubborn piece of data that simply will not fit. The cosmos, it seems, still has the capacity to astonish us, to whisper that our understanding, however sophisticated, is always provisional. This humility is not a surrender, it is the essential fuel for the next great leap. It is what drives us to look deeper, to question more fundamentally, and to remain forever awestruck by the magnificent, puzzling reality we are privileged to inhabit. So we have traveled from the careful calibration of distant stars to the ghostly echoes of the Big Bang itself. This is not a single, isolated puzzle. The Hubble tension is a vast and intricate web where every thread of explanation pulls on another. It connects the painstaking precision of measurement with the deepest foundations of theoretical physics, binding together the fate of dark energy, the nature of gravity, and the very story of our cosmic home. This is where the frontier of knowledge truly lies, in that stubborn, electrifying space between what we know and what the universe is trying to tell us. The journey through these 25 reasons reveals a truth more compelling than any single answer, that the greatest discoveries begin not with answers, but with a profound and persistent question. As the James Webb Space Telescope and a new generation of observatories gather their next torrent of data, as theorists dream their most audacious dreams, we all get to be witnesses. Stay curious, follow the headlines from these magnificent missions, look up at the night sky and appreciate that you are living in a moment of magnificent, unresolved mystery, a chapter of the cosmic story still being written. And we would love to hear which of these reasons you find most compelling, which thread of the web you would pull on first. Share your thoughts in the comments below, and let's keep exploring this expanding universe